the planet that has only completed one orbit around the Sun since the invention of the telescope. Think about that for a moment. Every single astronomical discovery made since Galileo first pointed his optic tube toward the stars. Every comet, every asteroid, every distant galaxy, every nebula, every supernova, every exoplanet, every black hole, every gravitational wave, every cosmic microwave background measurement, all of it happened within a single Neptunian year. The entire history of modern astronomy, from the discovery of Uranus to the first image of a black hole, fits inside one trip this world makes around our star. And yet, despite being born of mathematics and pure human intellect long before anyone ever saw it with their own eyes, Neptune remains the least visited, least understood, and perhaps most violent giant in our solar system. This world was not discovered by accident. It was not stumbled upon by a lone astronomer peering through a telescope in a moment of serendipitous fortune. Neptune was found because the laws of physics demanded it exist. When Uranus was discovered in 1781, astronomers quickly realized something was wrong. The seventh planet was not behaving as Newtonian gravity predicted. It was wobbling, deviating, being tugged by something unseen out there in the cold, dark void beyond. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this mysterious perturber must be. They handed their coordinates to observers, and in September 1846, Johann Galle at the Berlin Observatory pointed his telescope to within 1 degree of Le Verrier's predicted position. There it was, a new planet, discovered not by sight, but by arithmetic. This was humanity's greatest triumph of theoretical physics, proof that our equations could reach across billions of kilometers and grasp the invisible. But Neptune does not care about our mathematical victories. It does not care that we found it with a pen before we ever saw it with an eye. This planet is a realm of extremes so violent that they defy terrestrial intuition. Its atmosphere is composed primarily of hydrogen and helium, but it is the trace amounts of methane that give it that striking azure color. Methane absorbs red light and reflects blue, painting the planet in hues of deep cobalt and ultramarine. But that beauty is deceptive. Beneath that serene blue veil lies the most turbulent atmosphere in the entire solar system, save for the Sun itself. Wind speeds on Neptune have been clocked at over 2,000 kilometers per hour, the fastest planetary winds ever measured. To put that in perspective, the strongest hurricane ever recorded on Earth, Cyclone Patricia, had winds of about 345 kilometers per hour. Neptune's winds exceed that by a factor of nearly 6. These are not gentle breezes. These are supersonic jets, screaming through an atmosphere of frozen methane and ammonia, ripping clouds apart and reassembling them in patterns that shift visibly over hours rather than years. The great dark spots that appear and vanish on Neptune's surface are massive storm systems the size of Earth itself. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's storms are transient and volatile. They appear, rage for a few years, and then disappear entirely. The most famous of these, the Great Dark Spot, observed by Voyager 2 in 1989, was a massive anticyclonic storm that stretched across 13,000 kilometers. By the time the Hubble Space Telescope looked for it in the mid-1990s, it was gone. In its place, new storms had formed. This is a planet that does not hold onto its features. It lives in a state of perpetual atmospheric revolution, churning and changing with a violence that makes the weather on Jupiter seem almost placid by comparison. But the atmosphere is only the thinnest skin on this world. Descend below those shimmering clouds, and you enter a realm of crushing pressure and exotic phases of matter. At depths where the pressure reaches millions of times Earth's atmospheric pressure, the hydrogen and helium mixture begins to behave in ways that cannot be replicated in any laboratory on our planet. The intense compression forces electrons to become unbound from their nuclei, creating a superionic state where hydrogen ions move freely through a lattice of oxygen and carbon. This is not a gas. It is not a liquid. It is a strange, conductive fluid that has been theorized to exist but never directly observed. Beyond that, deeper still, the pressure becomes so immense that carbon atoms are crushed into diamond structures. The conditions are right for diamond rain, where tiny crystals of solid carbon form in the upper atmosphere and precipitate downward through the layers like hail, only to be subjected to even greater pressures that may convert them into liquid carbon or even metallic carbon. The interior of Neptune is a geological foundry where matter exists in states that do not naturally occur anywhere on Earth. Neptune is the densest of the gas giants, which strikes many as counterintuitive. It is smaller than Uranus and significantly smaller than Jupiter, yet it packs more mass into a smaller volume. Uranus has a density of about 1.27 grams per cubic centimeter, barely denser than water. Neptune, by contrast, has a density of 1.64 grams per cubic centimeter. This higher density indicates a significantly larger rocky or icy core relative to its overall size. The leading models suggest that Neptune's core is composed of rock, metals, and water ice, mixed with methane and ammonia ices. And it may account for as much as 70% of the planet's total mass. That core is buried beneath 10,000 kilometers of atmosphere and fluid layers, making it completely inaccessible to any direct observation. But its gravitational influence shapes everything about the planet, from its magnetic field to its thermal output. And that thermal output is another mystery. Neptune emits approximately 2.6 times more energy than it receives from the Sun. Unlike Jupiter, which generates a significant fraction of its internal heat through gravitational contraction and residual heat from its formation, Neptune's surplus energy is more difficult to explain. It is so far from the Sun, 27 times farther than Earth, that solar radiation at that distance is only about 1/900th of what we receive. And yet Neptune radiates nearly 3 times that tiny input back into space. This is not a planet that is slowly cooling from its birth. Something inside it is generating heat, perhaps through the ongoing differentiation of its interior, where heavier elements continue to sink toward the core and lighter elements rise, releasing gravitational potential energy in the process. Or perhaps it is the friction of internal convection currents, the churning of that superionic fluid that acts like a dynamo generating the planet's magnetic field. The exact mechanism remains one of the enduring puzzles of planetary science. The magnetic field of Neptune is itself a strange beast. It is tilted at 47 degrees relative to the planet's rotation axis, and offset from the planet's center by about half the planet's radius. To visualize this, imagine Earth's magnetic North Pole located somewhere near the equator and shifted toward the surface. This extreme asymmetry produces a wildly complex magnetosphere that shifts and wobbles as the planet rotates. Unlike Earth's relatively stable magnetic bubble, Neptune's magnetosphere undergoes dramatic variations over the course of its rotation, channeling charged particles in paths that are constantly changing. The source of this chaotic field is thought to be the superionic fluid in the planet's mantle, where conductive layers are not distributed uniformly around the core. But why the fluid would produce such a lopsided field is a question that remains open, largely because we have only ever had one brief flyby to gather data. That flyby, conducted by the Voyager 2 spacecraft in August 1989, remains humanity's only intimate encounter with this distant world. The probe flew past Neptune at a distance of just under 5,000 kilometers from the cloud tops, taking measurements and photographs that would fill scientific journals for decades. It discovered 6 new moons, confirmed the existence of rings, measured the planet's rotation rate, and provided the only close-up images we have of this azure giant. But Voyager 2 was built in the 1970s. Its instruments were primitive compared to what we could launch today. Its cameras were slow. Its sensors were limited, and it was traveling so fast that its entire encounter with Neptune lasted only a few hours. Everything we know about the planet's atmosphere, its internal structure, its magnetic field, and its weather comes from that brief window of data combined with decades of ground-based observations from telescopes that must peer through Earth's turbulent atmosphere. The rings of Neptune are another feature that has only been partially observed. They are dark, tenuous, and composed primarily of organic compounds that have been darkened by radiation exposure over billions of years. Unlike Saturn's brilliant icy rings, Neptune's ring system is clumpy and incomplete, forming arcs rather than full continuous bands. The outermost ring, known as the Adam's ring, contains several bright arcs that have been named in honor of the planet's discoverers. These arcs persist despite the laws of orbital mechanics that should spread them out into a uniform ring over time. Something is shepherding these particles, holding them in place, perhaps a small moon or moons that orbit within the ring itself. The exact mechanism is still debated, because we have not observed the system long enough to track the evolution of these structures. The moon system around Neptune is dominated by Triton, a world so strange that it demands its own category of celestial object. Triton is not like the other moons of the outer planets. It orbits Neptune in a retrograde direction, opposite to the planet's rotation. This is a rare configuration that almost certainly indicates Triton was not born in orbit around Neptune, but was captured from the Kuiper belt, that vast reservoir of icy bodies beyond the orbit of Pluto. When this capture occurred, Triton's orbit would have been highly eccentric, stretching and squeezing the moon with tidal forces that would have generated enormous internal heat. That heat may have been sufficient to melt Triton's interior, differentiating it into a rocky core, a subsurface ocean, and a thin crust of nitrogen ice. Today, Triton has a thin atmosphere, composed primarily of nitrogen, with trace amounts of methane and carbon monoxide. It has geysers that erupt plumes of nitrogen gas and dark particulates, rising up to 8 kilometers high, before being carried by the tenuous winds. These geysers are powered by seasonal heating from the sun, even at that extreme distance, where surface temperatures hover around -235 degrees Celsius. Triton is so cold that nitrogen freezes solid into ice that is harder than granite at those temperatures. It is the only large moon in the solar system to have a retrograde orbit, and it contains more than 99.5% of all the mass orbiting Neptune. The other 13 known moons are tiny fragments, captured asteroids or debris left over from the planet's formation. But Triton is a world in its own right, larger than Pluto and comparable in size to Europa and Io. And then there is the question of Neptune's origin. The planet formed somewhere between 4 and 4.5 billion years ago, likely closer to the Sun than it is today. The standard model of solar system formation, the Nice model, named after the French city where it was developed, proposes that the giant planets underwent a period of dynamic instability that rearranged their orbits. Jupiter and Saturn fell into a resonance that pushed Uranus and Neptune outward into the outer solar system, scattering planetesimals and smaller bodies in the process. This migration explains the current distribution of asteroids and Kuiper belt objects, and it explains why Neptune ended up beyond Uranus, despite being the more massive of the two. But the details remain debated. Did Neptune form in place? Did it migrate? Did it exchange places with Uranus at some point in the distant past? The isotopic signatures in its atmosphere and the composition of Triton's surface could hold clues, but we lack the high-resolution data needed to resolve these questions. What we do know is that Neptune's existence has shaped the outer solar system in profound ways. Its gravity has sculpted the Kuiper belt, creating gaps and resonances that have shepherded countless icy bodies into stable orbits or ejected them into interstellar space. The extreme tilt of its magnetic field and the violence of its weather suggest that this is not a peaceful giant slowly cooling over time. It is an active, dynamic world where energy is generated internally and expressed in winds that would shred any spacecraft we could build. It is a place where diamonds rain from the sky and where hydrogen is squeezed into metallic states that conduct electricity without resistance. It is a world where time moves so slowly that one Neptunian year stretches across 165 Earth years, meaning that the planet has only completed one full orbit since 1846, the year of its discovery. The next time Neptune returns to the position in the sky where we first found it, the year will be 2011. That moment passed. The human fascination with Neptune is not merely academic. It speaks to something deeper, a recognition that our solar system is not a quiet, orderly place, but a chaotic realm of violence and beauty. Neptune represents the frontier, the boundary between the known and the unknown, the outermost major planet beyond which lies the Kuiper Belt and the vast interstellar void. It is a reminder that our perspective is limited, that the universe is full of worlds we cannot see and forces we cannot fully comprehend. When we look at that pale blue dot through a telescope, we are seeing light that traveled for over 4 hours across 4.5 billion kilometers to reach our eyes. That light carries information about a world that has been circling our star for 4 billion years, a world that will continue to circle long after we are gone. The storms will rage, the winds will howl, the diamond rain will fall, and Neptune will remain, an azure sentinel at the edge of the solar system, waiting for us to return.